Last topic for this section of dynamics. So gravitational field strength, lesson 7. Our goal is to calculate the gravitational field, aka gravity, of objects using the universal gravitational constant. So what you need to know is that gravity is equal to the gravitational field strength. So these words are kind of interchangeable. As you move away from the center of the Earth, we know the gravitational field, aka gravity, decreases in magnitude but not direction. It's still attracting you towards, the Earth itself, the center of the Earth. Gravitational field strength is different for different planets and moons. So, force of gravity, we have two different formulas that we know of. We have our original, where Fg was equal to mg. And we also have that Fg is equal to g m1 m2 over r squared. So we can make these equations equal to one another. So mass times gravity is equal to g m1 m2 over r squared. So there's a bunch of different masses floating around here. And basically what we can know is that if we're talking about a person on Earth or any other planet, we would talk about the gravity that that person is experiencing. So when we were calculating it using our Fg equals g m1 m2 formula, the person would be one of these masses and the planet that they were on was another one of those masses. And the radius between them would have been r squared. So if we say that m1 here was the mass of this person, and we're looking at the other side of the equation and we're calculating mg with the mass of this person, we could say that this would be m1. Because m1 appears on both sides of our equation, technically I could divide this side by m1, divide this side by m1, and they cancel. So we are left with g is equal to big G, m2 over r squared, where m2 is really the mass of a planet or whatever we are standing on in this case, planet or moon, I should say. And g, in our notes, he talks about it's the acceleration due to gravity. So we can use these interchangeably. All right, so just remembering that we can cancel and equate two equations because they were both equal to Fg. This becomes a really important concept a little bit later down the road, and for sure in Physics 30, being able to recognize that we can make these two equations equal. So what is the gravitational field strength on the surface of Neptune? So the gravitational field strength, we're looking for G. Therefore, we're going to say that gravity is equal to G, the mass of Neptune in this case, divided by the radius of Neptune squared. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of Newton was 1.03 times 10 to the 26 kilograms, all divided by the radius of Neptune, so 2.48 times 10 to the 7 meters squared. This ends up being 11.2 meters per second squared. Now, where did seconds come from? Don't forget that Newton is a kilogram meter per second squared. Now, in this case, we had a Newton times a meter squared per kilogram squared. Oopsie. So in our equation here, if I put that in for this big unit here, we would have a kilogram cancels on the top and the bottom. We get a meter cubed all over seconds squared kilograms. Our kilograms will cancel with kilograms on the top here, and we will end up with meters squared canceling here, and so we're canceling the 3 down to a 1, left with meters per second squared. So don't forget that a Newton is a composite unit. What is the gravitational field strength at a distance of 1.914 times, oh my goodness, 10 to the 7 meters above the surface of the Earth. And if a person weighs 400 newtons on the surface, what would they weigh at this distance? So our formula is G equals G, the mass of the planet, so Earth in this case, divided by the radius squared. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of Earth, which is on our formula sheet. So 5.97 times 10 to the 24 kilograms divided by, now our radius is the radius of Earth, so 6.37 times 10 to the 6 meters plus the distance we are from the surface of the Earth. And that's all squared. I get that G is equal to 0.6119 meters per second squared. So from here, what I did is I found that on Earth's surface, we have Fg equals mg. The force of gravity was negative 400 newtons. This person was being pulled down towards the surface of Earth. And we can go backwards to find mass, which was 40.77 kilograms. From there, at a distance above, we can take our new gravity force, our new value for gravity and calculate the gravitational force, okay, or weight. So 40.77 kilograms times 0.6119 meters per second squared. We could technically say that's negative because we are accelerating towards the Earth, just not nearly as strongly. And we get 25 newtons towards Earth. Surface, I guess I could say. Okay. There are only 5 questions for homework this time, so do all of the questions on page 24 of the workbook.